For a given grammar G and string W, does G generate W? For a given grammar G and string W, does G generate W? For a given context-free grammar G and string W, we can obviously check that if this string is generated by the grammar, so it is a decidable language. Method 1. Go through all derivations generated by G, checking whether any is a derivation of W. Since there are infinitely many derivations, this idea does not work. If does not generate, the algorithm doesn't hold. That is, this idea provides a recognizer but not a decider. Method 1. Go through all derivations, check whether any is a derivation of W. Since there are infinitely many derivations, this idea does not work. If it does not generate, the algorithm doesn't halt. That is, the idea provides a recognizer but not a decider. Method 2. Make the recognizer a decider. For that, we need to ensure that the algorithm tries only finitely many derivations. If a context-free grammar is in Chomsky normal form, then for any W, a string belongs to language of G, where W mod W equals to n, exactly 2n minus steps are required. This is an important thing. Exactly 2n minus 1 steps are required. Convert context-free grammar into CNF. For a string W of length mod W equals to n is greater than 1, list all derivations with 2 to n minus 1 steps. If n is less than equal to 1, list all derivations with 1 step. If any of the derivations listed above generates W, accept; if not, reject. Convert context-free grammar into Chomsky normal for a string W of length mod W equals to n greater than 1. List all derivations with 2 to 2n minus 1 steps. If n is less than equal to 1, list all derivations with 1 step. If any of the derivations listed above generates W, accept; if not, reject. For a given context-free grammar, G is language of G5. So emptiness problem. So it is decidable for context-free languages. Emptiness problem is not decidable for context-sensitive, recursively enumerable, and recursive languages. To test whether L of G, language of the context-free grammar, is empty, we need to test whether the productions of G can generate a string of terminals. Determine for each variable whether that variable can generate a string of terminals. When the algorithm determines that a variable can generate a string of terminals, the algorithm marks that variable. When the algorithm determines that a variable can generate a string of terminals, the algorithm marks that variable. The algorithm starts by making first all terminals, then it marks variables that have on their right-hand side in some rules only terminals. Determine for each variable whether that variable can generate a string of terminals. Uh, Determine for each variable whether that variable can generate a string for terminals. When the algorithm determines that a variable can generate a string of terminals, the algorithm marks that variable. The algorithm starts by making first all terminals, then it marks variables that have on their right-hand side in some rules only terminals. If the start symbol S is not marked, accept; otherwise reject. For a context-free language L and a string W, does W belong to L? That is, there is a context-free grammar such that W belongs to L of G. uh, and string W. Does W belong to L? So if we have a context-free grammar, then we can just trace it. So it is uh, if this machine accepts, if it accepts, if it rejects, rejects. So when we have this clarity, then the machine will accept. If it accepts, then it will halt in the final state. If it rejects, then it will halt in the non-final state. So in both the cases, we are able to tell clearly. So it is a decidable problem. For two context-free languages generated by two context-free grammars A and B, is L of A equals to L of B? If language this can generate all the strings, uh, this for two context-free grammars, if L of A equals to L of B, we can't do it, but why? EQCFG is equal to A comma B, A, B context-free grammars and L of A equals to L of A. Since the class of context-free languages is not closed under intersection and complement, we cannot use the symmetric difference for EQCFG. Since the class of context-free languages is not closed under intersection, and here we are saying if L equals A equals L of B, since the class of context-free grammars is not closed under intersection and complement, we cannot use the symmetric difference. The symmetric difference of A and B equals to L of A intersection LB complement union L of A intersection complement LB, and test if L of C is empty, and test if L of C is empty, and test if L of C is empty. But context-free languages are not closed under complement and intersection, and context-sensitive language is not closed under emptiness property. But context-free languages are not closed under complement and intersection, and context-sensitive language is not closed under emptiness problem. Hence, this is undecidable. If language of A equals to language of B is undecidable for even context-free language. Is it decidable whether a given context-free grammar generates a finite language? Checking if language of context-free grammar is finite is decidable. Is it decidable whether a given context-free grammar generates a finite language? Checking if language of context-free grammar is finite is decidable because we just need to see if language of context-free grammar contains any string with length between n and 2n minus 1, where n is the pumping lemma constant. If so, language CFG is infinite, otherwise it is finite. Decidable. Stack Overflow: let G be a context-free grammar and let us assume that it is in Chomsky normal form. If it's not, we'll convert it first. An important property of this normal form is that the only way to derive the empty word is with the single rule S0 epsilons, where S0 is initial. Thus any derivation adds some non-trivial part. Now let n be the number of variables in a grammar and let k be the maximal length. G generates an infinite word if it generates a word of length at least k to the power n plus 2. Decidable problems concerning regular languages. I think Hello. Decidable problems concerning regular languages. A, a DFA equals B is a DFA that accepts input string W. So it is decidable, we can easily do it. The problem of testing whether a DFA B accepts an input W is the same as the problem of testing whether B W is a member of language of a DFA. A language of DFA is decidable. We simply need to present a Turing machine that decides a DFA. Problem 2. B is an NFA that accepts input string W. NFA is decidable. We could design a Turing machine and that decides NFA. A regular R is a regular expression that generates string W. So it can also be done. So it is decidable. A is a DFA and LA equals to phi. A DFA accepts some string if reaching an accepting state from the start by traveling along the arrows of the DFA is possible. To test this condition, we design a Turing machine T. On input A, where A is a DFA, mark the start state of A. Repeat until no new states get marked. Mark any state that has a transition coming into from any state that is already marked. A and B are DFAs and LA equals to LB is decidable. Calculate symmetric difference. So it is decidable. LA equals to LB is decidable for regular. LA equals LB. LA equals LA equals LB. It is done possible for regular and DCFR. A equals to RS. R and S are regular expressions and language of R is subset language of S. LR is subset of L of S if and only if L is complement intersection. LR equals to phi. R and S are regular expressions and language of R is subset of language of S. Language of R is is subset language of S if and only if S, LS complement intersection LR. A is the DFA and language of A equals to sigma star is decidable. G is a context-free grammar that generates epsilon is decidable language. We can apply membership problem. Infinite DFA. The following team decides infinite DFA. It is also done. If A accepts infinitely many strings, it must accept strings of at least k length. M is a DFA that accepts some string containing an equal number of zeros and ones. Show that BAL DFA is decidable. Hence, theorems about CFLs are helpful here. So, if A accepts infinite, LA is an infinite language. Infinite DFA is equal to A such that language of A is infinite. The following Turing machine decides infinite DFA. If A accepts infinitely many strings, it must accept strings of length at least k. Let E equals to M. M is a DFA that accepts some strings with more ones than zeros. Show that E is decidable. Language of A. M is a DFA which does not accept any string containing an odd number of ones. This is a decidable language. Language of A. G. G is a context-free grammar over 0, 1 and 1 star integer G is not equal to 5. Is decidable. Contains exactly k strings where k equals greater than equal to 0 or k equals to infinity is decided. From my notes, halting Turing machine. M is a Turing machine and M halts on input. So a Turing machine will halt on some input that is an undecidable or recursively enumerable problem. M is a Turing machine and M halts on input W. M is a Turing machine and language of M equals to 5. Empty Turing machine. Undecidable. If language of M is 5, then it is undecidable. En Turing machine. M is a Turing machine and Lm complement equals to 5 is an undecidable, recursively enumerable. Lm is not equal. Language of M is not equal to 5. Empty. Not empty Turing machine. Undecidable. Regular Turing machine. M is a Turing machine and Lm is a regular language. Undecidable. Regular Turing machine. M is a Turing machine and Lm is a recursively enumerable. Undecidable. Not RE. Regular Turing machine. M is a Turing machine and Lm is a not recursively undecidable. Lm is not REC. L is M is a Turing machine and the language of M is a REC. Cursive language is undecidable. A Turing machine ever writes a blank symbol over a non-black symbol during the course of its computation. Undecidable, not enumerable. L3 G such that G is ambiguous, recursively enumerable, while L3 complement is not recursively enumerable. L3 is equal to G such that G is ambiguous, recognize, recursively enumerable, while L3 complement is not a recursively enumerable. No Turing machine is greater LBA. Finite automata plus 2 counter is greater NPDA. So Turing machine is greater than LBA, which is finite automata plus 2 stacks, and which is greater than NPDA, NFA plus 1 stack, which is greater than DPDA, which is greater than NFA plus 2 DFA. Any Turing machine with symbols and n states can be simulated using 4mn plus n states by other Turing machines. Any Turing machine with m symbols and n states can be simulated using 4mn plus n states by other Turing machines. If A is less than equal to P, B, A is a polynomial reducible to P. If A is not recursively enumerable, If A polynomial reduction B means A is polynomial reducible to B. A is polynomial reducible to B. If A is not recursively enumerable, then B is not recursively enumerable. A is polynomial reducible to P, but A is not recursively enumerable, then B is also not recursively enumerable. If A is polynomial, this B A dash. If A is a Turing recognizable, then A is decidable. Some decidable or undecidable problems. Language of M has at least 10 strings, is a recursively enumerable. Language of M has at most 10 strings, not recursively enumerable. L equals M. M is a Turing machine that accepts a string of length 2014 recursively enumerable. There are finite number of strings of length 2014. If we can execute multiple instances of Turing machine in parallel, if any string is accepted, we can stop. Language of M is recognizable by a Turing machine having even number of states. Language of M is recognized by a Turing machine having even number of states. Decidable. M does not modify the tape on input W. Decidable. Arbitrary Turing machine never prints a specific letter. Undecidable. Universal or total. So it has one accept, one reject. Okay, so and this X is an input to universal Turing machine, universal or total Turing machine, where N is binary coding of a valid Turing machine, where N is binary coding of a valid Turing machine. Hash is a separator. X is an input string to Turing machine M. X is a binary representation. X is an input string to Turing machine M. X is binary representation. We will simulate Turing machine M on X by universal Turing machine. If M accepts X, then universal Turing machine will accept M this X. If we will simulate Turing machine M on X by universal Turing machine, if M accepts X, then UTM will accept this. If M is not a valid representation of a Turing machine, reject it without doing any simulation. Decidable if the language or property has a total Turing machine. Semi if the language has just a Turing machine. Undecidable no Turing machine exists. Given a Turing machine A has at least 481 states. Decidable. A takes more than 481 steps on epsilon. Decidable. A takes more than 481 steps on some input. Decidable. A takes more than 481 steps on all inputs. Decidable. Property of a Turing machine to be part of our language. Property of a Turing machine to be part of our language. Has at least 481 states. By looking at the description of Turing machine M, we can tell how many states a Turing machine has. L equals collection of Turing machine takes more than 481 steps on epsilon. L equals collection of Turing machine takes more than 481 steps on epsilon. Run a Turing machine on epsilon and count the steps. This process will be completed in finite time for sure. If in 481 steps, if M on X has not reached accept or reject, it will take more than 481 steps. Note in UTM take one more tape that counts number of steps. A takes more than 481 steps on some input. Infinite strings are possible. Takes more than 481 steps. Suppose on epsilon Turing machine M takes only 60 steps and halts, but any other input may take more than 481 steps. In worst case, all the tried inputs look less than 481 steps, but we cannot stop because any input among we didn't try may take more than 481 steps. In worst case, Turing machine will always keep running and keep checking. Method 2. Take all the permutations of inputs of length 481 and run inputted Turing machine M only on these inputs. Given a Turing machine whichever moves its head more than 481 tape cells away from the left and marker on input epsilon. It's decidable because we can check for all the possible combinations of number of heads can be moved into number of states into number of ways each cell can be modified. Elements distinctness problem. A Turing machine M is given in a list of strings. A Turing machine M is given a list of strings over 0 1 separated by this as follows. Its job is to accept if all the strings are different is decidable problem. His job is to accept if all the strings are different is decidable. P is such that P is a polynomial with multivariable with an integral root is recursively enumerable but not recursive. P is a polynomial with single variable with an integral root. Recursive. G is a connected undirected graph. Decidable. M. L1 M is a Turing machine. M is a Turing machine and there exists an input on which M halts in less than M steps. M is a Turing machine and there exists an input on which M halts in less than M steps is a decidable problem. There exists an input on which M halts in less than these steps is a decidable. It first finds the length of this and stores it. Then it runs M on all inputs of length at most this for at most these steps and accepts if M accepts at least one of the strings within the specified number of steps. L of M. M is a Turing machine. A language of M is less than equal to 3, not recursively enumerable. Language of M contains at most 3 strings. It's not recursively enumerable. We have to check that this Turing machine M won't accept more than 3 strings. That is not possible. After checking 1 crore strings, maybe it will accept fourth string. Hence, it's not recursively enumerable language. M star that semi-decides the language, runs M on all inputs in an interleave mode, and halts whenever three inputs have been accepted. Notice that M this generates the input strings for M one by one as they are needed. It's not allowed that M star first generates all strings and then starts running M on them, since generating inputs takes infinite time. L4 M is a Turing machine that accepts all even numbers. Not recur. It keeps running to check if TM rejects at least one even number, not recursively enumerable. L5 M. M is a Turing machine. LM is finite, not recursively enumerable. M is a Turing machine and Lm is infinite. M is a Turing machine and Lm is countable. This is the language of all Turing machines. Since there are no uncountable languages over finite alphabets and finite length strings. L8 M is a Turing machine and Lm is uncountable. This is empty set. There are no uncountable languages over finite alphabets and finite length strings. Is uncountable. L9, M1, M2, M1 and M2 are two Turing machines and epsilon gives L of M1 M star that semi-decides the language runs the two machines on epsilon. It interleaves the run between the machines and accepts them but not recursive. Linear bounded Turing machines and recursive Turing machine. A Turing machine consists of a finite control. A Turing machine consists of a finite control, a tape and a head that can be used for reading or writing on that tape. A Turing machine consists of a finite control, a tape and a head that can be used for reading or writing on that tape. A Turing machine consists of a finite control, a tape and a head that can be used for reading or writing on that tape. The Turing machines form a stable and maximal class of computational devices in terms of the computations they can perform. A Turing machine M does not accept W if the machine either halts in a non-accepting state or does not halt. A general-purpose Turing machine is called usually a universal Turing machine, which is powerful enough to simulate the behavior of any computer, including any Turing machine itself. If we increase the read-write number of heads or make the tape two or three-dimensional, the Turing machine will at most speed up the operation of the machine while it not increase the computing power of doing something more than the basic model. This set of languages accepted by non-deterministic Turing machine is same as the set of languages accepted by deterministic Turing machine. The set of languages accepted by non-deterministic Turing machine is same as the set of languages accepted by deterministic Turing machine. The set of languages accepted by non-deterministic Turing machine. The set of languages accepted by non-deterministic Turing machine is same as the set of languages accepted by deterministic Turing machine. In linear bounded automaton, the length of the tape is restricted. A linear bounded automaton. A linear bounded automaton is a non-deterministic Turing machine which has a single tape whose length is not finite but bounded by a linear function of the length, whose length is not infinite, whose length is not infinite but bounded by a linear function of the length of the input string. If L is a context-sensitive language, then L is accepted by a linear bounded automata. The converse is also true. Recursive and recursively enumerable languages. A Turing machine M decides a language L if when started with input W it always halts and does so in a halt state. If it accepts W, it halts in an accepting state, and if it does not accept, it halts in a non-accepting state. A Turing machine M decides the language. If it halts in a accepting state, and if it does not, if it halts in an accepting state, that means it, and if it does not accept, it will halt in a non-accepting state. But in either cases, it will halt. A Turing machine M semi decides the language L. If when started with input W, it halts if and only if it accepts W, otherwise it does not halt. A Turing machine M semi decides the language L if when started with input W, it halts if and only if it accepts W, otherwise it does not halt. A procedure for solving is a finite sequence of instructions which can be mechanically carried out given any input. An algorithm is a procedure that terminates after a finite number of tests for any input. A recursive language. A language L is recursive if there is a Turing machine that decides it. A language L is recursive if there is a Turing machine that decides it. Or a set X is recursive if we have an algorithm to determine whether a given element belongs to X or not. Recursive enumerable language. The language L is recursive enumerable if and only if there is a Turing machine M that semi-decides it, or a recursive enumerable set is a set X for which we have a procedure to determine whether a given element belongs to X or not. Every recursive language every recursive language is recursive enumerable, but the two classes are not the same. Recursive language is subset recursive enumerable proper subset. The class of recursive language is a proper subset of the class of recursively enumerable languages. The class of recursive languages is a proper subset of the class of recursively enumerable languages. The class of recursive languages is a proper subset of the class of recursive languages is a proper subset of the class of recursively enumerable languages. If L is a recursive, then its complement is also recursive. So recursive are closed under complement. A language is recursive if and only if both it and its complement are recursively enumerable. The class of recursively enumerable languages is not closed under complement. A language is generated by a grammar if and only if it is recursively enumerable. Recursively enumerable are the type 0 languages. Recursively enumerable are type 0. If L1 is not recursive and there is a reduction from L1 to L2, then L2 is also not recursive. If L1 is not recursive, if L1 not recursive and there is a reduction from L1 to L2, then L2 is also not recursive. A context-sensitive language is recursive. There exists a recursive set which is not a CSL. Closure properties of recursive and recursively enumerable languages. Recursive languages are closed under all except halting problem. Halting machine takes an input and encoding of a Turing machine and an encoding of an input string and returns yes if M halts on W and no of M does not halt on W. The halting problem is undecidable. There exists no Turing machine that decides it. The halting problem is undecidable. The halting problem is undecidable. That is, there exists no Turing machine that decides it. There is no Turing machine that halts on all inputs and always says yes. If M halts on W and always say no if M does not halt. Halting problem is undecidable. There exists no Turing machine that decides it. The following problems of Turing machine are undecidable. Given a Turing machine does M halt on the empty tape? Given two Turing machines M1 M2, do they halt on same input strings? Given a Turing machine M, is the language that M is semi-decides regular? Is it context free? Is it recursive? Reduction. To solve a problem B is undecidable, start with an instance of a known undecidable problem. Create an instance of problem B such that the answer to the instance of problem B gives the answer to the undecidable. If we could solve problem B, we could solve halting problem. This problem B must be undecidable. If we can reduce problem A to problem B and problem A is undecidable, reduce problem A to problem B and problem A is undecidable, then B must also be undecidable. If we can reduce problem B to problem A and problem A is undecidable, then it tells nothing about problem B. So this is